Okay, good afternoon, everyone. Could you please press the thumbs up sign if you can hear me and you can see the screen with with our webinar, Institute of Mathematics webinar series. Okay, thank you very much. So again, good afternoon and welcome to the third webinar in the IMath Webinar series for this semester. So I would like to remind everyone that this webinar is being recorded and being streamed live via YouTube, and the link will be posted on our official IMath Facebook page. So our speaker for today is Mr. Jake Avila. He is an instructor of the Institute of Mathematics and a member of the Differential Equations Academic Group of the Institute. So today he will talk about his work titled Homogenization of a Quasi-Linear Elliptic Problem in Domains with Small Holes. So let us all welcome Mr. Jake Avila.
Sir Gina, share ko na po yung screen ko. Nakikita na po yung screen ko, sir?
Yes, nakikita na po.
Okay. Thank you, Sir Gino, for the introduction. So for today, I will talk about our work with Between on the homogenization of some PDEs with quasi-linear coefficients in domains with small holes. So we will start with some background first on the homogenization theory, and next I will present the problem that we will be solving along with some data assumptions, and we will proceed with the method of homogenization. In particular, I will focus on the periodic unfolding method, and towards the end, we will give some convergence results and some possible extensions. So here, I have a carbon fiber reinforced plastic, which I refer to as CFRP. So this is a material which combines carbon fibers embedded on a matrix plastic in a form of resin. So this combines the properties of both the carbon fiber and the plastic. So this is known to be strong, durable, and lightweight. So in fact, it will be used on the new vehicle series of BMWs this year. This types of materials posits the following questions. Well, first, how can we describe these CFRPs, knowing the individual properties of our carbon fibers and our plastic? And moreover, the second question, we just don't want to describe, we want to quantify. For example, if we know that carbon fiber has property A and your plastic has property B, what is now the effective or the resulting property of your CFRP? So is it just a simple sum or some kind of relation? So basically, these are the questions that homogenization theory wants to answer. So by definition, this is a branch of mathematical analysis which treats the asymptotic behavior of PDEs with, of course, your usual differential operators, the gradient, the divergence, or Laplacian. And these PDEs, the variables contain highly oscillating coefficients. So meaning they vary, the values of these coefficients vary. And from there, the goal of homogenization is to describe the macroscopic or the global behavior of a material by taking into account its microscopic or local properties. So that is our goal for today. So in a nutshell, here are some celebrities in our area. So we have Ma'am Patricia, Sir Alain, Ma'am Doyna, all our French mathematicians. Of course, we also have their US counterparts and some in India and so on. Actually, some of them actually visited the institute in the past. So, but basically, the area of homogenization was popularized by the discovery of composite materials around the industrial era during the 1960s. So these are kinds of materials which are fine mixture of two or more individual components that are combined to produce a material with an effective property or a desired property. So it is known that these materials, these composite materials, have a better property than the individual components combined. So in effect, these effective properties also determined on how these materials are combined. For instance, we want to know the geometry. Is it stacked? Is it weaved or interlaced? Or it is embedded in a matrix and so on. So these all affect the effective property of the material. So from there, some examples of composite materials. Well, for instance, we have our CFR piece, and another example.
Hi, Jake. Sorry to disturb. I think may may concern ata na freeze daw yung slide.
Wait lang, sir.
From my side, yeah, I think naka-freeze na din. That was...
Dito na ba tayo, sir? Yes.
Yes.
So, siguro kung nag-freeze, wait lang. Ay, nawala yung option na Siguro ganito na lang muna. Kung nag-freeze.
Okay. So, will this be okay with everyone? Para... press the thumbs up sign. Okay, so okay lang naman po.
Okay. So, to continue, some examples of composite materials. For example, here, the one used for high-speed internet, we have for fiber optics, and the one that makes these kinds of complicated structures possible in the form of fiberglass. So this one is the Haidar Center in Azerbaijan. So in particular, in this work, we are interested with the following materials. So here we have a metal, and we introduce perforations or holes in this metal. And some types of this is called a matrix composite, where we fill these holes with another material. So from a mathematical point of view, if we want to model these types of material, we want to be as close as possible to the geometry of our material. So in particular, we will start with an open and bounded subset omega of Rn with a Lipschitz continuous boundary, denoted this symbol. So it is assumed to be Lipschitz. Well, first, it will be necessary for our preliminary results later. And from an application point of view, not all boundaries in nature are smooth. So to account for corners or even edges, we assume the boundary to be Lipschitz. Then from there, we will introduce these reference cells or these squares. Then we will collect those that are inside, and we will color them light blue. And those that are inside omega but intersect the boundary, we will color them gray. And then from there, we will go back to this fixed domain omega later. We will now introduce these holes. So let us look at this reference cell, this square. We will introduce two small holes with period epsilon, meaning they are distributed. The distance between two corresponding holes is epsilon, and they are small in a sense that their sizes are less than epsilon. So for instance, this blue hole is of size epsilon delta 2, and this one, this orange hole is of size epsilon delta 1. And we will collect all these blue holes, and we will call them our Dirichlet holes. And then these orange holes we will call our Neumann holes. And then from there, we will define the following sets. So the collection of the perforated reference cells, so meaning these light blues, all these copies that are inside omega, we will call that omega epsilon delta 1 delta 2. And those collections of the blue boundaries, we will call that the boundary of T epsilon delta 2. And those collection of your orange boundaries, as well as the boundary, the whole boundary of omega, we will call that the boundary of omega epsilon delta 1, 0. So now that we have in place all the notations and our sets, we are now ready to define our PDE. So this one, if you can see from the application, so this looks like more or less our metal foam. And then from there, So we will consider this problem, this quasi-linear PDE for a non-negative gamma. So this models the stationary heat diffusion in a composite. So essentially, this is the microscopic behavior of our material. And here, if we will interpret this in the context of a stationary heat diffusion or heat propagation, F is a known heat source acting on this set. And U here is the temperature. A is the thermal conductivity of the material, which depends on its position on this set and also on the temperature. So this dependence is known as the quasi-linear one. And we will call A the gradient of U its flux. And then from there, we will prescribe a Dirichlet condition on this boundary. And so that says that your temperature is 0 on this boundary, and we will prescribe a nonlinear Robin condition on this boundary. So here, essentially, it's a combination of both nonlinear Dirichlet and nonlinear Neumann. So for this problem is motivated with the following. For first, it is known that your thermal conductivity A can depend in a nonlinear way on temperature, as to Bendib in 2004. So specifically, for example, for glass or wood, the dependence is nonlinear increasing. For ceramics, it is decreasing. And for aluminum or some kind of semiconductors, it is actually not even monotone. So this motivates the study of quasi-linear coefficients involving problems in heat diffusion. And also some related models in our work. This can also solve the stationary reactive flow of a confined fluid in omega epsilon that are reacting on the boundary S epsilon. So for different values of G here, for instance, if G is this one, for alpha and beta positive, this is known as the Langmuir kinetics model. And for this one, for P between 0 and 1, this is your Freundlich kinetics model. So P here is called the order of your reaction. So now that we know the problem that describes the macroscopic behavior of our material from the application perspective, let us now go to its mathematical aspect. So in particular, let us go back to our problem P. So we know, since the temperature varies in our set, and also as well with the thermal conductivity, we know that the flux here is discontinuous. Also, that is due to our the nature of our domain. So in that regard, we know that this problem do not admit a classical or a C1 solution. So our goal now is to define another space which we can find a solution. In particular, let us recall the following spaces. Well, first, we have for P in 1 to infinity and F a measurable function, we'll define the following space LP of omega to be a collection of all functions F such that this integral is finite, and L infinity of omega, basically the collection of all bounded functions almost everywhere in omega. And here is now the space where we can find the solution. So this is called the Sobolev space H1 of omega, which is the collection of all square integrable functions whose derivatives in the sense of distributions are also square integrable. So from there, let's have the following assumptions on our data. So first, F is square integrable, and then on omega, and then G is also square integrable in the boundary of T, and then tau is positive and bounded in the boundary of T, and H is C1, that is increasing and satisfies a growth condition. So meaning its derivative is bounded. And here for the thermal conductivity A, it is elliptic and bounded. And it is periodic, Carathy-Dory, meaning it is measurable in the first variable and continuous in the second variable. And its modulus of continuity satisfies some conditions that will be useful later on the proof of uniqueness. And then lastly, delta 1, delta 2, and epsilon satisfy these two limits, which are both finite. So we will call this limit of K1 as the critical size of your Dirichlet small holes, and this one, K2, is the critical size of your Neumann small holes. It is critical in the sense that the Lebesgue measure of the boundary of these holes remains bounded by strictly positive constant if the size is critical. And if the sizes are smaller, then the solution will converge to 0 in H1. And if the sizes were bigger, the solution will diverge in H1. So that is critical in that sense. So from there, we will now define the following spaces. So first we have V epsilon delta 1 delta 2, which is a subspace of H1 of omega epsilon delta 1 delta 2 such that it is 0 on these boundaries. And it is equipped with the following norm. So from there, we are now able to convert our original problem P to its variational or weak formulation. And dx here is your usual differential, and your d sigma x is your surface measure acting on these boundaries. And from there, we can show that this variational formulation is well posed. So the existence of the solution follows from Schauder's fixed point theorem, and the uniqueness from some arguments in quasi-linear matrices involve Q's Lebesgue dominated convergence theorem, and the stability is straightforward from known inequalities. Okay, so now that we know that we have a weak solution to our problem, which describes the microscopic behavior of our material, our goal now is the following. So we ask the following questions. So una, do we expect that our weak solution converges to some limit function? And moreover, is that limit function also solves some PDE, which will now describe the macroscopic behavior of our material. Or in other words, now that we know the properties of our heterogeneities, how can we describe the homogeneous version of our material? So in order to do that, we need some method of homogenization. So here are some methods that are developed in the past. Well, we have for the non-periodic case, meaning the heterogeneities or the holes are distributed in a random fashion. So we have the G, H, and gamma convergence developed in 1967 to 1973. And then for our case, for the periodic case, we will have the Tartar's method of oscillating test functions, which uses some extension operators. And then the multiple scale method, which uses asymptotic expansions, and then the two-scale convergence. And in particular, in this work, we will focus on the last, the periodic unfolding method, which was recently developed in 2002. So we will focus here because mainly it has some nice properties. So first, the convergences are in LP spaces, unlike in others. And we know that the convergence in LP spaces are very rich. We know a lot about it. So this makes the proofs easier to handle and becomes more elementary. And then we also have the two-scale. We don't need a notion of a two-scale convergence. We also need a weak convergence. And any function in the perforated domain is mapped in the unfolded function of fixed domain. And then lastly, unlike the Tartar's method, we do not need any extension operators for non-homogeneous boundary conditions. So that's why we are using this method. So now that we know that we will use the periodic unfolding method, let us now introduce the operator. So before that, let me just go back to the fixed domain omega and let us name the following sets. So individual squares, here we will call y, and those copies of y that are completely inside omega, we will call that omega epsilon hat. And those copies of y that are inside omega but intersect the boundary, we will call that lambda epsilon. So from there, we can now define the unfolding operator. So for Lebesgue measurable function phi of x in omega, its unfolding is given by the following. So phi of epsilon times the greatest integer function of x over epsilon plus epsilon y. For points in this set and 0 on this set. So we can see here that essentially what it does is it maps x to this expression here. So the main motivation being this x over epsilon we can interpret as the integer component of x over epsilon, and then y here as the fractional component of x over epsilon. So to have a more clearer view, of what is happening, let's have the following illustration. So for a point in R2, say 1.5 negative 2.1, and when we consider epsilon equal to 1, and y here is your unit square, let's have the following. So essentially, this unfolding, this part here tells us that we can decompose x into its integer part and its fractional part. Okay, so that is what it does to a single point x. So now we know, what it does to a point. Let's now level up a little bit. Let's look at what it does to a function. So in particular, I have here the graph of sine x. So let us now look at what it does to what is the unfolding of sine x. So here is the graph of the unfolding of sine x for epsilon equals 0.5. So we can see that your sine x here is embedded in R2. However, your unfolding is embedded in R3. And here we can see that the unfolding operator introduces these folds in our graph. So mainly because this is due to the greatest integer part of the definition. And as epsilon becomes smaller, say epsilon equals 0.45, these folds become smaller as well. And as epsilon goes to 0, we can see that our folds get smaller and smaller in a way that our graph is being unfolded to another graph whose projection on the xy plane is actually the original graph of your sine x. So this is how the unfolding operator works in our case. So now that we know the action of our unfolding operator in fixed domains, so to have this work in our case, to adapt this in our domain that we have earlier, we will use the following extensions developed in 2008 and 2015 respectively. So the one with 2 parameters and the other with 3 parameters. So after using this, we will have some convergence results. Before we go into that, let me just mention some related works in this area. Well, first we have the boundary value problems in domains with fine-grained boundaries. So this is the work on Marchenko and Krylov in 1974. So this is the first time we consider small hosts in PDEs. And next, for this work by Mamchernescu and Mura in 1982. So loose translation would be a strange term from somewhere else. So this is the time where we had critical size for your Dirichlet small hosts. And then for this one, for the non-homogeneous Neumann by Konka and Gonato in 1988, this is the time where we had the critical sizes of your Neumann small hosts. So it is to be noted that in these two works, the method of homogenization is used, is the Tortas method of oscillating test functions. And recently, the first time it was applied, the periodic unfolding operator, or the method was applied to homogenization of Neumann problems was in the work of Ud Hamoda in 2011, where he considered a Neumann boundary condition. And for a linear coefficient as well as a Robin boundary condition for small hosts using the unfolding operator, it was done by Ud and Hamoda in 2015. So in our case, it is the first time where we will apply this to quasi-linear problems and the more general boundary conditions than the one considered by Ud and Hamoda. And so that is basically what is new in this work. And now we are ready to show or to give our convergence results. So here for gamma equal to 0 and H homogeneous of degree 1, first observation is that our weak solution converges to this limit function u sub 0. And this u sub 0 here solves this PDE, which is free of epsilon and now describes the macroscopic behavior of our material. So from a numerical point of view, this is easier to model or simulate using your usual methods. And again, U naught here is a temperature, not just on our defined sets, but on the whole of omega. So this is actually the global behavior of our material. And then again, A-hom gradient of U sub 0 is the flux. And then A-hom here is now the effective property. So we will see later what is its its expression. No? And then the contribution of our Robin holes, no? The Robin boundary condition is this term, and of course this term as well. Then F here again is your known heat source, and then this zero order strange term, K1 squared theta u sub 0. Theta here is a non-negative function which can be interpreted as your local capacity of your Dirichlet holes. And then this is called a strange term, no? So medyo related ito dito sa work nito, na itong pangalawa, no? It is the strange term which only appears when we are in the case of small holes. So it is strange in that sense. It does not appear when the sizes of the holes is just a period. No? It only appears when we are in the case of small holes. So we also have that on the boundary of omega, u sub 0 is 0 as well. So this now represents the macroscopic behavior of our material for gamma equal to 0. And for gamma positive, the only difference is that this term vanishes. Okay. So from there, here is now to answer our question earlier. So what is the relation of our individual properties to the effective one? Well, here is the expression of the effective property. So it is some mean value of this expression here. Of course, Kai here solves some cell problems involved in this PD as well. So some possible extensions of the work include the following. So first, we can consider some corrector results. Actually, we are in the process of completing these results, and we can also consider some optimal controls or some approximate or exact controllability problems. And lastly, instead of your heat source F to be in L2, we can consider a more general setting where your data is from L1. Okay, so here are my references. And so for more details, you may look at this paper here. And thank you for listening.
Okay, thank you very much, Mr. Avila. Can you all please give Mr. Avila a warm round of virtual applause? Thank you. Okay, so the floor is now open for questions from the audience. So you can raise your hand, okay, you can unmute, or you can type your question in the chat box. So meron po tayong question kay kay Ma'am Fulgencio. Rhea?
Hello, good afternoon. First, Jake, sobrang ganda ng presentation, so good job. Well, I have one question lang. Kasi first time ko maka-encounter talaga yung small holes. Although, nakita ko na yung title ng paper na French yung sa strange term, pero hindi ko alam na small holes pala siya. So, yung question ko lang is, curious ako kung ano yung main difference ng una, pagpapakita ng existence and uniqueness ng solution kapag small holes or wala bang difference dun sa normal. And pangalawa, ano yung, yun din sa small holes, ano yung difference niya sa homogenization? Kasi yun nga, first time ko talagang makita to.
Okay, so for, thank you, Rhea. So for the first question, the proof for the existence and uniqueness is essentially the same. We will only introduce a change of variable. For instance, we know that x is so kasi pag sa yung usual parang y yung ginagamit natin na variable. For small holes, we will just introduce a change of variable y equals delta z. So parang they're still the same.
Yeah, okay.
For example, elliptic will still use lax milligram and so on and so forth.
Mm-hmm.
For the second question, for the homogenization part, there are key differences. Mainly, we will need to the first, the properties. Show ko na. So first, the properties will be redefined. Yun yung una. So magbabago silang lahat. Will be more specific kasi magkaroon nga tayo ng change of variable. And we will need to define new sets para magkaroon tayo ng limits. And yun nga, para mapalabas natin yung strange term. Yun yung main difference.
Okay. sige. Kung wala na question, pwede pa ba ako magtanong?
Go lang.
Sorry.
Yes, go ahead. Go ahead.
Okay, so kasi na-mention mo yung L1 data. Gusto mo ba mag-work about that?
Actually, right now, pina-finalize pa namin naman between yung ano.
Ano, hindi naman ngayon. Parang sa future, ganyan.
Yeah, pwede. Yes, of course.
Okay, sige. Noted. Thank you.
Okay.
Okay, that's good. Thank you, Dr. Fulgencio. So actually, question ano, so doon sa main theorem, yung nabanggit mong convergence, that converges in LP, right? Doon sa page 3, piece.
This one? Or
yes.
sir.
So kapag ba ganun, ano, so nako-converge siya sa kahit sa LP kahit anong P yan.
In
So
particular,
mapa P greater than 1 or infinity. Sorry?
P equals 2 po dito, sir, sa...
P equals 2 ang gamit niya. Okay. Okay. Tapos, so ano yung ano, sorry, na-curious lang ako. So ano yung interpretation natin doon sa ano, doon sa strange term mo na nabanggit na nag-a-appear siya sa...
bigla na lang siyang lumalabas pag parang kunyari ang sizes ng holes mo, sir, ay pareho lang sa period. Kunyari pareho silang epsilon, no? This term does not appear. Nagkakaroon lang siya ng appearance pag dumikit ka doon sa critical sizes ng small holes mo. And ito yung parang contribution ng small holes mo, no? And yung theta here yung parang local capacity ng holes mo. Parang ganun. Ganun siya in-interpret.
Okay. Thank you very much. Do we have any other question from the audience? Okay, Sir Ernie po. Sir?
Hi, Sir Ernie.
Hello, good afternoon, Jake. Meron kang term doon kanina na yung delta 1 and delta 2 mo related sa epsilon. And I noticed that yung isa raised to the power n, tapos yung isa ay n over 2.
Yes, sir.
Itong relationship ng delta 1 and delta 2 with epsilon, optimal ba ito na nakuha ninyo na order 1 siya, no? Yung decrease niya ba, if you divide by epsilon, then it reaches it tends to a positive limit or possibly 0, no? But yun lang, yung epsilon na ito, na epsilon to the 1, ito ba'y importante doon sa ano ninyo, or is it interesting also to investigate whether this can be epsilon to some other power? Nagmamatter ba yan? Sorry. Thank you.
Actually, no, this K1 and K2 here are not actually from us. No, this is from these two works. This is from the first K1 is from this work, and then the K2 is from this work. No? So they have proven that is the critical, or that is the most strict bound, no, for delta and epsilon. For the case of Dirichlet, so ito yung para sa K1 na limit, and then for the case of Neumann holes, doon naman po yung nakuha yung K2. So yun na po yung pinakasagad na bounds.
No. Yung tungkol yun sa K1 and K2, no? Pero essentially what you're saying is yung growth at which nagte-tend to 0 yung delta 1 at delta 2 is of order 1 with respect to epsilon. Or rather, hindi siya order 1 kasi may power din si delta. Pero yung ganong relationship, crucial ba yun? Siyempre, result nila yon. But when, siyempre, you piece together these results, dapat makita mo rin yung proof nila, di ba? Super crucial yung ganong relationship.
Actually, at this point, I'm not sure about the answer, no? But yeah.
Okay, thank you. But I think it's maybe interesting also to look into this. If you ano ba uli yung could you help me recall what ano yung delta 1 at delta 2 in relation dun sa problem setting?
Delta 1 and delta 2 is yung sizes po ng holes. Ito pong isa ay epsilon delta 1 yung size, and then yung isa naman po epsilon delta 2.
Yun nga no. So parang interesting na bakit ano. And then yung isa n over 2, no? So meaning one has to be half as small as the other. Yun ba yung more or less parang ganun yung sa
Actually,
power.
sir, parang dun sa previous papers po, ang notation po kasi ay R epsilon. So parang ngayon recent lang nag-introduce ng delta. So in a sense, parang dati, ano talaga, alam na alagin yung order talaga nung convergence.
I see. All right. Thank you.
Okay.
May pahabol pang, yes, may additional questions si Rhea.
Yes po, sorry. Last na.
No problem.
Ano,
Go ahead.
yung first yung sa delta, napansin ko pala yon yung sa K1, kasi 'di ba n over 2 siya, tapos pwede n equal to 2, 'di ba? So paano yung K1 kapag n equal to 2? Ha?
N greater than 2 siya.
Kailangan strictly greater than 2. Okay. Sige, yung isa pang question, kasi ito ay 'di ba, perforated domains. Pwede ba na yung two component domains yung gawan ng ganito?
Yes, pwede.
Yan. Kasi yung sa kanina mong application, meron kang holes, tama ba? Yan. Tapos si isa ay inserted. So, yung inserted ay pwede siyang considered na two component domain kapag conductor din yung ini-insert. So, yan. So, isa ba siya sa plans nyo na gawin in the future?
Yeah.
Yes, question mark.
Ang ginagawa namin right now is this one.
Yung, alin? Yung two component domain.
For two component na small holes.
Okay, sige.
Insertion.
Okay, sige. Exciting. Thank you.
Okay.
So thanks again. Do we have any other question? Okay. So kung wala, thanks again to Mr. Avila. Palakpakan po ulit natin siya. Bigyan po ulit natin siya ng virtual applause. And thank you to the audience for your attention. Okay, so our next webinar will be on after the election, I think. So mga bandang May 16 na tayo magkita ulit. Okay, so just punta na lang po tayo sa IMath Facebook page for any further announcement. Okay, so again, thank you to Mr. Avila, and then we'll see you again next time. Goodbye.